Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's get started. Welcome to Microsoft Research Colloquium. And today we're thrilled to have Yair Weiss here to talk about compressed sensing and natural image statistics. There's so much to say about Yair. In his early career, he worked on layer representation for videos, which really created a new era for vision too. There's a bunch of problems to work on. And then later he worked on belief propagation and really he made very big impact in this area to make BP algorithms theoretically, a lot of theoretical contributions, but also pushed applications in vision. There's so much to say because we collaborate on papers. We work together. I really enjoy working with him. But if one thing I want to say, talk about him is, when I supervise students, I ask them to look at model papers when they are, working for deadlines. And to me, the first paper I could think about in computer vision is Yair's 2001 ICCV paper on deriving intrinsic images from video sequences. And that says a lot about his work in vision and learning. Okay, Yair.
Thank you very much. Thank you for the introduction. I want to thank you all for coming on this beautiful day when I'd much rather be outdoors, but hopefully it will be something of interest. So I was asked to prepare a talk that would be accessible to a very broad audience, and I thought I'd talk a little bit about compressed sensing, which is certainly the most dramatic topic that I'm working on. So I'll spend just the first at least 1/3 of the talk will really not be about my own work, but just explaining what compressed sensing is. And this picture over here, let's see if I can make this work.
Excuse me, sure. Most of this broad audience isn't, the broadness of the audience hasn't showed up.
Yes. So the picture that you're seeing here is from the L1 Magic website, which I highly recommend. So the compressed sensing, I'll talk about in a little bit what it is. It's a very interesting set of mathematical results, but also it should be said in their support that Donahoe, Candes, the people behind this are strong believers in reproducible research. And so they set up a very nice website where all the software is available. And this is the picture from that website. One thing I'd like to point out is, this is a set of mathematical results, compressed sensing. But even though it's about math, really you can see that natural images are front and center on this web page. And that's really what the focus of my talk, the last 2/3 of the talk are going to be, is whether really natural images are a good fit to this beautiful mathematics. And I'll show, as several others have shown, that there's really a disconnect between what the math assumes and what natural images are really like. And the last half or third of the talk, depending on the time, is about our work, actually the work of Hyun Chang, who just recently graduated here at MIT. Many people here have probably seen him walk around the lab. He's sort of a quiet Korean student who comes to talk to me, where we've tried to propose an alternative to compressed sensing that could actually be relevant to natural images. Okay, what better scientific resource than Wired magazine? So what is compressed sensing? I'll just read. It's a paradigm-busting field in mathematics that's reshaping the way people work with large data sets. Only 6 years old, compressed sensing has already inspired more than 1,000 papers and pulled in millions of dollars in federal grants. In 2006, Candes's work on the topic was rewarded with a $500,000 Waterman Prize, the highest honor bestowed by the National Science Foundation. It's not hard to see why. Imagine MRI machines that take seconds to produce images that used to take up to an hour, military software that is vastly better at intercepting an adversary's communications, and sensors that can analyze distant interstellar radio waves. Suddenly, data becomes easier to gather, manipulate, and interpret. I like how money This is America, right? So it's all about the money. 500,000, millions of dollars. But really, I guess we had a Waterman Award winner speak here 2 weeks ago, Scott Aronson. It really is a tremendous honor. And it really, I mean, very serious people also, not just Wired Magazine, will agree that there's really very significant mathematical results. So let me just explain these two, in 2 slides, what compressed sensing is. And so it really deals with a very simple problem. So I give you a signal x, and I multiply it by a matrix A, which gives you the vector y. And the question is, can you recover x from y? And if we know anything from linear algebra, then we know that if A is a square matrix and it's invertible, then of course we can invert it. But what if it's a rectangular matrix? So the dimension of y is much smaller than the dimension of x. So sort of most people would tell you you cannot, because you have a null space, there's an infinite number of possible x's that could have caused the same y. And really the main result of this field is that if you also have an additional assumption, namely that x is k-sparse, so that's what this stem plot is supposed to show you. Here's a signal. It has some 512 elements, but most of them are 0, and only a small number are non-zero. So if k is the amount of non-zero elements, you can still exactly recover x. And A is a random matrix, meaning its elements are sampled IID. So it's really just a random matrix. As long as the number of measurements grows faster than k log n, then you can exactly recover it by solving a linear program. So not only is the information there that allows you to recover it, you can even do it very efficiently. You could imagine doing this by some combinatorial search algorithm. Right? You can search over all n strus k possibilities for the non-zero coefficients, but these theorems tell you don't even need to do that. You can just solve a convex optimization problem and get x exactly. Okay, so that was the result in 2 slides. And again, because they have this beautiful website, you can actually download the code. And if you don't trust the mathematics, you can actually try this for yourself. So here's a proof by MATLAB. I take the signal over here. It has, I think, 512 elements in it, but only some fraction of them are non-zero. I multiply it by this random matrix, and you can see that it's a rectangular matrix. So there's only it's a 100 by 500 matrix. So I've lost a lot of information. I solve this linear program. It takes 0.31 seconds on my laptop, and voila. The original x is on top. The estimated x is in the bottom, and everything's fine. So it really works. Not only is there math behind it, but it really does work.
There's an extra line, though. Why is there that extra line on the bottom that's not on the top? Over there.
Where? Oh, sorry. It not only works, it's even useful to capture people in the audience who are not paying attention. Okay. So there are a lot of interesting math. This is certainly a very deep and interesting mathematical result. There are a lot of mathematical results. What is it about this particular mathematical result that made Wired Magazine call it paradigm changing and so on and so forth, and millions of dollars in federal grants? Really, one of the main motivating examples has always been natural images, because if you take a natural image, like this famous image over here, and you do something called a wavelet transform on it, it doesn't really matter for the sake of this talk what it is, but there's some change of basis that you can change from the sort of a trivial basis for images is you think of it as a matrix where every pixel is an element in the matrix, but you can also think of it as a vector of coefficients in some basis. And if you look in that basis called the wavelet basis, and you plot a stem plot like I plotted earlier, you can see that indeed only a small fraction of the coefficients are significantly non-zero. So this seems like a great match to the theory in that it would allow us to now capture images with a small number of random measurements. And people have picked up on this idea. This was one of the top 5 inventions of the year, according to Technology Review in 2006. It's called the single pixel camera. It's a very clever idea that shows you how you can capture images rather than with an ordinary camera, you just directly capture random projections of a scene. So the way it works is there's a lens over here, and then they use these micro mirrors such as exist in projectors, modern projectors, and each of these projectors can be either oriented towards the sensor or away from the sensor in a random fashion, and this implements a random projection optically before you actually do an analog to digital. Before you ever have the image in digital form, you can already do a random projection. Now you can ask, if you have a cell phone, you know that you can get a 5-megapixel camera for, I don't know, maybe $10. So why do you really want to build this compressed sensing camera? And this was pointed out by several people, that maybe a better application of this theory to natural images is not so much in minimizing the number of pixels, but in minimizing the power consumption. So this is a very nice recent paper by Oyke and El-Gamal, where they show that basically by using random projections, you can get cameras whose power consumption is 2 orders of magnitude less than standard cameras. And essentially, the power consumption in these cameras, if designed correctly, goes with the number of projections. And here's a quote from a recent IEEE Spectrum article on their work. This is not from their paper, but from the IEEE Spectrum. It says, "You merely pick random combinations of pixels and sum their intensities. Amazingly enough, with a sufficient number of such measurements, but far fewer than the number of pixels, you'll have enough data to reproduce the original image." Okay, and again, this is an example of the more popular press really being very excited about this. But if you actually look at the papers and see the images that they get out, they don't look very good. So this is from the single pixel camera paper. And there's the original on the left and the 40% compression. I want to emphasize this is not a factor of 40 compression, but rather 40% compression. So really, the number of measurements here is about half the number of pixels. It's not at all a dramatic savings. And the result really looks pretty bad. And if you remember the math, you would think, oh, shouldn't the reconstruction really be perfect? And it's far from perfect. So what's going on here? And I think the problem is the popular press didn't read the fine print. And so it's important to read the fine print. And this is, again, from the L1 Magic website. And I'll just read. Here is an example. The 1 megapixel image below has a perfectly sparse wavelet expansion. It is a superposition of 25,000 Dobschi 8 wavelets. Instead of observing the image directly, say we took 100,000 random measurements, i.e. we're given the projection onto a 96,000 subspace. I don't know what happened to 4,000, but never mind. Then we look for the image whose wavelet transform has the smallest L1 norm that has the same projection onto the subspace. The measurements agree with what we have observed. The result is below. As we can see, the image has been reconstructed perfectly. So the good news is here we have perfect reconstruction with a factor of 10. So this is really dramatic. This is what we'd like. But where's the fine print?
Where was the factor of 10?
So we went from 1 megapixel to 100,000, or 96,000, depending on. Where's the fine print? This is not a real image. What was done here was they took the image, found its wavelet representation, found the 25,000 most strong elements, and zeroed out all the rest. And that's the image that they're showing us here. It's not the original image. It's actually an image that's been pre-processed in a way so it's exactly sparse. And in fact, if you look, I didn't want to belabor this point, but if you look at almost all the papers written by mathematicians on compressed sensing that have images in them, it's always this is what they do. They take the original image, they throw away all but a small number of wavelet coefficients, create a new synthetic image, and work with that.
But as a compression algorithm, like suppose I just did that previous picture, viewing this as a compression algorithm, how good would it look if I tried to compress?
No, it looks very good. So in fact, this image, what you're seeing here, is after the compression, after all but 25,000 have been zeroed out. And it is...
But you're compressing it further with the fact that...
No, but the fear is that the noise in the remaining things that aren't zeroed out, these will interfere with your compression and what you read. If you didn't zero these things out...
It was already compressed before. They're just reconstructing it.
But
No,
you're
but I'm
compressing
saying,
it further,
but I'm saying
right?
if you didn't compress it before you ran this thing, then you might get no garbage, right? That's
That's what I'm going to show, yes.
But out of curiosity, I mean, this could still improve the compression if you've zeroed these things out, right? Or
Yes, it will improve it by a lot. The question of if that's valid, if you're allowed to do that. Because in the real world, you're not going to be dealing with these synthetic images. You want to design a camera that will take an image of a real scene, not a...
If your actual image isn't sparse, then like you're not going to end up with
Okay.
the best sparse
If you want the power
reconstruction of
savings,
it.
right.
Sorry?
You mean if you want the power savings, right? I mean, like
Yeah, if you want to really build...
the storage, it would be fine to strip out the.
Oh, yes, this is a very important point. I'll say this now. The whole point about compressed sensing is you want to do the compression before it's in the computer. Shah, maybe this answers your question. If what you want is just to take an image and compress it, it's already digitally in your computer. Just use JPEG. None of this theory is really relevant. The whole point here is you do this before you acquire the signal, and that's what allows you to save power. And the point is that this is not something you can really do before you have it in the computer.
Well, is there any hope of designing some physical lens or something which will take the spectrum and throw out the small coefficients?
Maybe. It could be very difficult. I think that's actually an interesting direction to go. No. I mean, part of the beauty of compressed sensing really was always that they use linear projections. And they say linear is very easy to do in physics. A lot of physical processes are linear. Something like this that is nonlinear is much harder to do. But yeah, Henry, maybe you have an idea.
For audio, it's easy though. Like for audio, all you want to do is just have some sort of lowish pass filter, and it's easy to construct circuits which actually will specifically do that. They'll just kill off that.
No. Anything linear is not going to do it. You need.
No. It's a nonlinear. It's like a
low pass is a linear filter.
I think we should.
which a threshold.
Yeah.
No, it's a threshold. Yeah.
All the restricted isometry stuff, that all doesn't just deal with sparse things, but also deals with reconstruction for something that's approximately sparse.
I'll talk about that in a
Where you
second.
say, so is this saying that the hypothesis is that the restricted isometry property doesn't apply for the real world, or?
Let me keep going, and I'll hopefully answer this question. Okay, so actually, again, I just want to emphasize that there's nothing, of course, this talk is publicly available, so there is nothing wrong or misleading about what's written in the L1 Magic website. They have this caveat, which I'm going to read now. It says, in the real world, signals and images are not perfectly sparse, and there is always some degree of uncertainty in the measurements. Fortunately, the recovery procedure can be made robust to these types of perturbations. See the stability and statistical estimation papers for details. And again, this is what I think Henry is referring to, that there are additional mathematical results that show that even if the signal is not perfectly k-sparse, then things do not break catastrophically. However, there's a difference between not breaking catastrophically and actually being useful from an engineering standpoint. And just to illustrate that, let's just take an image and not do this pre-processing trick. Just run the compressed sensing as is directly on the images without zeroing out anything. So this is the image. And this is when you do a compression to 15%, so approximately a factor of 10. So again, nothing breaks catastrophically. You're getting something that looks like the original image. It has a lot of artifacts. I doubt that anyone would pay money for this particular kind of camera. But it's not breaking catastrophically. Here's another one. Oops. This is with 25% random measurements, so it's getting much better. Again, it's not breaking catastrophically. You can see the original image. So I think, again, it's important to say that it's not the case that once you add a little bit of noise, all hell breaks loose. But it is important to go back and compare this to much more trivial things you could do. So here's something very trivial. You can take this image, and I just want to retain 10% of the information. How can I do that in the easiest possible way?
Low resolution.
Even easier. I'm just going to take every 10th pixel. Just take every 10th pixel, and then I'm going to reconstruct by linear interpolation. I'm not going to do any of this L1, blah, blah, blah. Just linear interpolation between the samples. So this does much better than the random projections followed by L1 minimization. And with 25%, again, the effect is even more pronounced. So just this interim summary, the dramatic results of compressed sensing are for ideal sparse signals. There is some extension that shows that things do not break catastrophically for things that are approximately sparse, But that results are no longer nearly as dramatic. That is, for many signals, what you can get with random projection followed by this L1 minimization is far worse than what you could get with much simpler techniques. And I should again add that this is, it's more of, if you read the original papers, not only do they have these caveats, some of the authors of the compressed sensing theoretical papers, like Justin Romberg, this Lustig et al. Paper is co-authored by Dave Donahoe, have pointed this out themselves, that when you actually want to run something like compressed sensing on more realistic signals, you should not use random projections and L1 minimization. But I think somehow this message has not made it all the way to the popular press. Okay.
Just as a curiosity, I mean, you don't want to do any pre-processing on the image.
Right.
But could we have done some post-processing rather than just take the L1 minimizer?
Yes, so that is something they do, and that can improve a little bit. I mean, you can basically take this result on the right and run denoising on it, and depending on how good your denoiser is, you can get very good results. But of course, you can also do it on any other technique. It is possible if you have a very good denoising algorithm to improve these results, but that has a lot less to do with the compressed sensing as much as it's a lot more to do with the denoising. Okay, so what's wrong really? Again, I think Greg alluded to this, and I think I did this on purpose by going fast. I said wavelets of natural images tend to be sparse. They're not really sparse in the mathematical sense. They're sparse in the statistical sense, meaning if you look at wavelet coefficients, you have a small number of coefficients that are significantly non-zero, but basically all the coefficients are non-zero. You don't have any, unlike this ideal sparse signal on the left, where some are exactly zero and some are strong, and natural images, all the coefficients are non-zero. It's just you have a small number of significantly non-zero. And that really breaks a lot of the beautiful, dramatic mathematical results. So what do we know about real natural image statistics? Again, this is a very well-studied topic. And if you look at wavelet statistics, there are, I guess, two things that people will say. One is that if you look at the distribution of coefficients, you have what's known as a statistically sparse distribution, meaning these are heavy tail distributions that are peaked at zero, but they're very different from these idealized. This is a histogram. So in a sparse distribution, you have two spikes, one at zero and one elsewhere. That's not what real signals look like. They have this kurtotic distribution, but it's peaked at zero, but there's not a spike at zero. That's one thing. The other thing that's different between these idealized signals and image wavelets is that there's a way to order the wavelet coefficients according to spatial frequency, and then the variance decreases. So it's not only that you have a small number of coefficients that are significantly different from zero, you know in advance which ones these are. They don't occur anywhere along the signal. There's a way to sort them so that the strong coefficients will always occur on the left with high probability.
So when you say sorting, it's not like it's sorted based on the amplitude, it's sorted based on some other...
Right, you sort on the spatial frequency. So every one of these wavelets has a frequency associated with it. If you sort according to that, not according to the value of the wavelets, you're right, otherwise it wouldn't be very, very surprising, yes. Okay, so what do we do? So how are we doing on time? Good. So I don't want to spend all my time just talking about negative results. I want to show some positive results. Yes?
Can I just ask one more question? So is it, if they had done L0 minimization, which is not convex, but would that have solved their problem, do you think?
No. I'll talk about this that's a good question. It's really about the measurements losing information, not about not the decoding algorithm. In fact, part of the nice results they show is that for certain class of problems, L0 and L1 are the same. Again, that's a very beautiful, unexpected mathematical result. So they can actually show that they're not losing any. There's a small regime in the middle where the L0 and L1 are different. But for a lot of these signals, L0 can be shown to be equivalent to L1. Okay, so I wanted to talk.
With regards to natural statistics. I mean, those are mathematical results, but for the...
Yes, that's true.
But if you did the L0 for the natural statistics, because you're arguing about the statistical level of sparsity, and that's more like L0. I mean,
yeah, it's L0 would behave. I mean, of course, you can't really do it. But
Yeah, but if you could do it,
even if you could do it, that's what I'll argue, it's not going to work well. You've lost a lot of information in the projections, basically,
oh, I see. Because of I see. Yes.
that you simply cannot recover, even in an information theoretic setting. Okay, so some positive results, or at least. So what can we do? So this got us thinking. So if you abstract a bit, what is compressed sensing? It says I'm going to take my signal, multiply it by a matrix, and I'm going to reconstruct using some additional knowledge on the signal. So and specifically, they say let's use a random matrix A, and we're going to use L1 minimization for the reconstruction algorithm. But let's abstract that out and assume that you're allowed to multiply by any matrix that you want. And your reconstruction algorithm can be as complex as you want. In fact, you're going to do the Bayesian optimal reconstruction given the measurements. What's the best matrix that you could use under these settings? So here's, it's a very easy to describe problem. I give you a signal that I tell you the distribution over signals. And I'm giving you some budget, say, of number of measurements that you're allowed. Design a matrix A so that when I multiply A times X, and I get Y, the mutual information between X and Y will be as large as possible. There's a technical restriction here is that you can make the mutual information be arbitrarily large by multiplying A by a constant. So we disallow that by basically the trace of A transpose A. That's like the total energy in your matrix, the sum of the norms of the rows. So every measurement you could think you pay according to how much, according to the norm of the rows, the sum of the norm of the rows, and we're going to constrain you to have a limited power budget. What's the best matrix you could design?
It's a limited power. Why can't you just make it proportional to A then? The identity?
Sorry?
It's dimension constrained to something.
Yes, it's dimension constrained as well, yes. A is P by P.
Then why does, if it's dimension constrained, why does the trace constraint matter?
Because you could take any matrix you give me, I'll multiply it by 100. The mutual information is going to go up. It's a fact about mutual information that it's unbounded as you. So we don't want to allow that. And also in a sort of a more practical setting, if you think of the matrix A as being something like radiation or something, it makes sense to constrain that. Anyway, so I think what's interesting about this.
Just curious, X is coming from a distribution, or you're assuming some form
Yes.
to the distribution?
X is coming from the distribution.
High
High-dimensional distribution that you know. I'm going to give it to you for free. And you just need to design the matrix A that's optimal for that distribution. And what's interesting about this is you would think this is a very easy criterion to write down. You'd think it would have been solved in the 50s or something. Everything's linear here. It's very easy to write down. I just multiply A. I want to find the matrix A so that when I multiply A by X, the mutual information between X and Y is as large as possible. But I want to convince you that it's actually much harder than it seems. So let's do some examples. Okay, here are some examples of signals. I'm going to test the audience to see if you can design a matrix. So here's some samples. Here's more samples, more samples, more samples. And I'm going to give you a budget of 2 measurements. Okay, so you can either measure individual coordinates if you want, or you can measure averages of coordinates. But you don't, if you measure an average, they have to be L2 normalized. So you can decide if you want to measure, say, a random projection, or if you want 2 random projections, or you can take the average of all the coordinates, the difference between the first coordinate and the second coordinate. I give you 2 of these measurements, and this is what the class of signals looks like. What would you do?
Show us the whole thing. How many are there?
Something periodic?
Well, so one thing I hope you can see is that most of the action in the signal is on the left-hand side of the signal.
It's a question. Is this a trick question, first of all?
No.
In the first 2.
Yes. So in fact, these are samples from a Gaussian distribution that has decreasing variance. So it has more variance on the left than on the right. And so the optimal thing to do in this case was solved more than 50 years ago. It's called principal component analysis, which in this particular case would tell you to measure the left 2 coordinates of this thing. Okay, here's another set of set of samples. Oops. Okay, what do you think?
Like indicators of the half-lines.
So one thing I hope you can see is, again, the variance decreases. So when this is a very sparse distribution, unlike the Gaussian. When there is a spike, it's tends to be much larger on the left than on the right. So again, if we were to do principal components, we would get the same answer as before and would say measure the first two. In fact, the best two projections for this case, yeah, sorry?
So what's the measure of inaccuracy or whatever? So if in the signal, the entire weight was on the first component, and I gave you as a thing something which had 50-50 on the first and the second, or let's say all of it on the second component.
Yes.
Would that be a close match or a terrible match?
You can do this. Let's assume that the squared error in your reconstruction is what we're. You take the vector in Rn and measure a squared error.
So whether you put all your mass on the second or the 50th doesn't make any difference. It should have been on the first.
In this particular case.
Or in a hypothetical example.
Is it an earth mover metric, or is it like
No, it's just the norm of the vectors, the Euclidean norm of the vectors. So you have to get it correct.
Right. Okay.
In fact, I'm going to show you now that this metric doesn't really matter because I can design two projections that will get it exactly right for this particular signal.
What I don't understand is, for all we know, it could be that the last bit, by looking at the low ordered, digits of that, tells you everything about the signal. And you can't really tell from these pictures, right? It could be that measuring the last bit is the best. You can't see in the picture, but there's a slight amount.
Yes, that's true. I'm in the real.
By linear measurement.
In the real world, I'm going to give you the full distribution. So if that's the case, you would know it. I'm going to give you the full distribution. So in this case, I'm telling you the way I generated this distribution is I first choose a random coordinate, and to turn on, and if I turn it on, I give it either +1 or -1 times some variance term that decreases. So it's either +1 or -1 at the very left, or +0.1 or -0.1 on the very right. That's the true distribution.
Times a Gaussian.
Sorry? No Gaussian in this case.
No Gaussian.
It's either +1 or -1.
But then you're,
So just measure the sum of all the coordinates.
the sum of all of them will tell you?
somewhat, yeah.
Tell you exactly what it is.
Yeah.
Yeah, so basically with two random projections, doesn't really matter. You can also do it in other ways, but if there's no noise, you're right, you could even do it with one projection. But suppose I make it Gaussian distributed, unlike what I do here, then even then, two random projections will give you perfect reconstruction. Doesn't matter if you're using L1 norm, L2 norm to measure, you'll just get it perfectly. And what's the worst thing you can do under this case is measure the first two coordinates. So here, PCA, which was optimal for the previous thing, is actually the worst possible thing you could do. Because what happens if you do PCA, you'll get it right only if the spike happened to be in the first two, and you're totally blind everywhere else. So it's actually the worst possible thing you can do. So I hope I've convinced you that this is a non-trivial problem. It's not totally clear what the right thing is to do. Okay, so in his thesis, Hyun made a lot of efforts in trying to solve this problem, but in particular, we considered the following set of signal models where every coefficient is drawn independently from some some distribution, which could be either sparse or dense. So it could be very sparse, like here on the left, or less sparse, like here in the middle and on the right. So it's a statistical sparsity. That is, every coefficient is independently sampled from this distribution, and the variance could either be the same along all coordinates or change as you go from left to right. So this is a class of signal models that includes the two things I showed you earlier. The first one I showed you was a Gaussian with decreasing variance, so it'd be a non-sparse distribution with a particular sparsity pattern. And this one is not exactly, the one sparse signal you can approximate by sampling every coordinate independently from a very, very sparse distribution. And for this class of signals, we want to find the matrix A that maximizes the mutual information between X and Y. I forgot to say that this problem was actually the first formal definition of this problem is from 1990 by Linsker. He called it Infomax. And he showed that the solution for the case of the Gaussians, which is indeed the principal component analysis. So principal component analysis can be derived in all sorts of ways, but among other things, it solves this Infomax problem. If I give you k measurements for a high-dimensional Gaussian distribution, the best you can do in the mutual information sense is to measure the first k principal components, and that's.
So what context was this work done?
It's a good question. It's about it's in computational neuroscience. So his claim was that sensory systems in the real world should have representations that maximize the mutual information from what's going on in the outside world and in the brain. And that's where he formulated Infomax, and he was trying to solve it analytically, and he solved it for this particular case. But until Hyun's thesis a few years ago, there has been no solution for anything other than the Gaussian to show you how difficult this is. It really seems misleadingly simple because you can write down the problem very easily, but it's very hard.
So Gaussian means each coordinate is Gaussian, and you know the variance.
Yes, and it can be a multidimensional Gaussian. It doesn't have to be IID.
Oh, it doesn't have to be IID.
Yes, but you can. That's not hard to find the coordinates. Yeah. Yeah, if it's along the standard axes, then the best thing to do is to measure the standard axes. But if it's along other dimensions, then you measure those k directions. Okay, so here are some results that Hyun managed to get. And these are all asymptotic results, but they are globally optimal. So one is in the case where the variance is the same along all dimensions. And turns out for a broad range, it doesn't matter what the distribution is, as long as the variance is the same in all directions. These are called white signals in signal processing. Random projections are optimal. In fact, you can also think of deterministic matrices that, I mean, it's not if and only if. There may also be deterministic for certain k and n, certain particular dimensions. He's also managed to work out deterministic constructions that are as good as the random ones, but at least asymptotically, the random ones are always optimal.
No, this is Nick.
You can imagine having some super kind of deterministic setting where you make sure that kind of your second moments all do what you want, but
again, the assumption is that there is some basis along which every coordinate is sampled IID.
I see. Okay. So this is
basically like Gaussian.
So it includes this very sparse distribution, but yeah.
I believe it now. Sorry.
I guess since this was not supposed to be a technical talk, this is related to the fact that people like Dasgupta and others have shown that random projections make things Gaussian. So if you take any high-dimensional distribution and you project it down with a random projection, it becomes Gaussian, a multidimensional Gaussian. And the Gaussian is the maximum entropy distribution, and that's really where it comes from. But anyway, we had to work a lot harder than that because a lot of those results only work when the number of projections is much, much smaller, grow sublinearly with dimension, and this result actually holds in a much broader setting. Okay, the other thing that he can show is that if you have a very skewed variance, it doesn't have to be Gaussian anymore, but if all of the energy is, say, on the left, the predominant energy is on the left-hand side, you might as well measure the left-hand side. And again, we can show this. So PCA projections are optimal, even when the signal is not necessarily Gaussian, but if the variance is very skewed. Okay, but the problem is that images are neither of those two cases. So again, images, when sorted accordingly, do have a skewed variance distribution, but they're not that skewed. They're certainly not Gaussian, on the other hand.
So the skewing you were hoping in the previous slide was exponential or something?
Yes. It depends on, okay, this is the sparsity level. If it's a Gaussian, and even if it's not skewed, then it's still optimal, right? Even if it's very, very narrowly skewed. So the point is, the sparser it is, the more you need, it needs to be more skewed. So we have this general theory on the one hand that doesn't directly hold for natural images. We have a different result that holds for what he calls multi-resolution signals. These are signals that natural images do fall into that category that have a natural band structure. So if you sort these coefficients in a particular way, they will be divided into separate bands, and every band has the same variance. And that ends up allowing us to prove an asymptotic result, which shows that the optimal thing are these band-wise random projections. So you basically have some set of random projections that only look at the first two coefficients, another set of random projections that only look at the next two, and so on and so forth. And the number of random projections per band will depend on this, how sparse the signals are. And it's actually, you have to solve a linear program just to figure out how many projections per band. But we can do all of that, and we do have something that is asymptotically the optimal way to sense natural images. So now we can look at some examples. And I think one important thing to realize, again, so I talked about all the ways people can play a little bit with the examples in order to get good results with compressed sensing on natural images. One way is by choosing the image. So you'll often see this cameraman image on the left in compressed sensing papers, which of course was taken, I don't know if you can see it's on the MIT campus. It was taken, I think, on the soccer field where they just had the memorial service this afternoon. That is an extremely sparse image. So this JX number is what's known as the neg entropy. It's the distance, the KL divergence between the distribution of coefficients and the Gaussian. So 0 would be Gaussian. The higher that number is, the more non-Gaussian it is. So the cameraman is a very non-Gaussian image. If you look at another more standard image, perhaps like this one over here, which, by the way, the copyright of this image is owned by my university, the Hebrew University of Jerusalem. So these are more typical images. They have a negative entropy that is smaller. That is, if you look at the cameraman, it really has this big piecewise constant areas, partly because it's a very old image, and so a lot of discretization effects are there, but real images are less sparse. If you look at this, then you see very different results. So in the cameraman, so these show the PSNR, so high values are good in the reconstruction. This is the fraction of pixels, of measurements over pixels. So this is very high compression ratios here, and this is a factor of 2 compression. And the red is PCA, and the green is random. So for the cameraman image, at least after some compression ratio, actually random projections do work better than PCA because it's a very sparse image. It's close enough to this regime of ideal sparse signals. For the Einstein image, that's never the case. PCA is always better to do. So, of course, Hyun's theory, which optimizes to the particular distribution, is better than both. Well, they're very close to PCA in the Einstein. So he uses the JX equals this particular. He optimizes his matrix for a distribution over coefficients that has either this distribution or that distribution in the two cases. So you're right, it's a form of cheating because you assume that you know for every image the distribution of coefficients. A more interesting example, let me just show. The other thing, although it's better, these are not huge effects. So if you look here, these are the reconstructions, and I guess you were asking about the post-processing. This is doing this, what's known as total variation denoising afterwards. So all the algorithms are doing a little bit better than simple L1 would have predicted. So in PCA, the results look very good in the sense that there's no artifacts, but there are no high frequencies. So if you remember the MIT campus, there should be columns here, but you don't see them because they've been blurred out. In this bandwise random projections, you see the high contrast columns here much better. And the random has more high frequencies, but it also has a lot more artifacts here. So
in these cases, if you applied the same pressure again and again, do you get a fixed point, or do you?
I don't know.
I mean, it's quite likely that this cameraman image already went through PCA at some. Somebody might have done it earlier, right?
Yes, it certainly went through all sorts of cleaning effects before they digitized it. Yeah, my guess is that you would converge to something that's very sparse, that wouldn't look like the original image, but would be a fixed point.
Also in these images, so using the same number of projections?
Yes.
Okay, but
5,000 in this
in
case.
terms of the quality of reconstruction now, I mean, PCA is going to be best for probably mean squared error. Is that true? Or, I mean, because we can visually look at these things, but if you're talking about quantitative reconstructions, which is what you're optimizing, how different?
So, okay, these are the numbers down here.
Because
These are these numbers. The PSNR numbers, the higher the better. So PSEI is better than random, and these bandwise random is even better.
so you're measuring the.
PSNR is the log of the mean squared error negative.
Oh, okay, okay.
So it's like the mean squared error, but in logarithmic coordinates, and high is good as opposed.
Under just Euclidean norm.
Yes. Under Euclidean. I should say that PCA is not necessarily optimal when you do nonlinear reconstruction, even in the mean squared error sense. Right? If you remember the previous example with this very sparse signal, you could get 0 mean squared error with random projections. PCA is optimal in terms of mean squared error when you do linear decoding.
Your reconstruction is
Nonlinear. Yes. And it's the same for all the algorithms. Okay, but in general, images have a range. They can be highly sparse, like over here, or a lot less sparse, like over here. And on average, this neg entropy is around 0.5 or 0.6. So the cameraman is really an outlier. And if you look at Lena, which is what we started with, it has, again, something like 0.5 because of all this hair over here, which really kills or the feather, sorry, which really kills this sparsity assumption. So let me just finish with showing the results on this since we started. So this is compare sensing with 25% random measurements. And this is reconstruction from PCA with the same number of measurements. And it's really much, much better, both in PSNR and in terms of visual quality. To implement this in hardware requires very clever engineering to do all these micro mirrors to get the random projections. To implement this in hardware, you just defocus the lens, and you have a low-pass filter. Because
That's assuming that you know the distribution of coefficients?
No, so PCA for natural images, it's always going to be equivalent to just blurring the image. You measure the low spatial frequencies. This has to do with the fact that the distribution is stationary. So you don't really need to know anything about the images. For any stationary distribution, the principal components are sinusoids. So this is very easy to do in engineering. You don't get to be labeled the invention of the year, but it does work a lot better.
Say power like you would with other things?
You could, but the gains in this case, the power consumption gains that you tend to get are the same as the factor of the compression ratio. So getting this factor of 4, I don't know how many people would be willing to do it. But I think if we could do a lot better than that.
Your battery lasts 4 times as long.
Yes. This is also true, by the way, in this megapixel battle. The old cameras had longer battery life. So if you're just willing to live with a 1 megapixel camera than an 8 megapixel camera, you have 8 times more battery life. But for some reason, consumers haven't figured this out. And but yes, you could. I think there is a.
There's many images which are much worse.
Well, if you're just going to mail them, email this later, it's the 1 megapixel is okay. People have written about this megapixel arms race, whether it really makes sense. But anyway, I think there is room for some of these ideas to make it into low power consumption batteries. We're not quite there yet. Okay, let me end. I think one take-home message. Yeah.
So you didn't give your bandwidth for the BWPCA? You didn't tell us how does your thing perform on this?
In this case, it's the same.
I see. Okay.
Again, because if the images are the number of bands allocated to the low spatial frequencies are all of them basically. It again depends on this JX number. If it's very close to if it's close enough to Gaussian, then it's skewed enough that PCA is the optimal thing to do.
How does it compare to JPEG?
Yeah, I should show that. So it's much worse than JPEG. This again is this point that Chang was asking about earlier. JPEG is a nonlinear compression algorithm. So you can basically get, for this image, you can get similar quality with, say, a factor of 10 compression, not a factor of 4, if you're willing to do nonlinear compression.
Is nonlinear the same as saying it's somehow, I mean, these are oblivious compression algorithms. They don't know what the image is, they just do the same thing. Whereas JPEG, I take it, sort of looks at the image in order to determine how to compress, or?
No, nonlinear really means nonlinear in the sense that, for example, if you could take the coefficients, a very good compression algorithm is to project it, threshold, and then do run length encoding on that.
That would be nonlinear.
That would be nonlinear because of the thresholding operation. And I think in that sense, there is a great opportunity from an engineering standpoint to do interesting things. If you really want to get power consumption down, you should think about doing nonlinear. If you could do nonlinear thing before the digital part in the analog domain, you could do very interesting things. Much better than our approach, because we're constrained only to linear. But for some physical standpoints, linear makes sense. So light tends to operate linearly, or waves, and so on and so forth. Okay, so one take-home message I hope that everyone here who leaves this room will then go on and spread is that it's important to realize that the very dramatic theorems of compressed sensing really hold for ideal sparse signals, not natural images. There are additional theorems that hold in the non-ideal case, but they're not a lot less dramatic. They don't give you anything, the same sort of magical feel that you get with the ideal sparse. No one would have a website called L1 Magic for the results with the for the non-ideal sparse signals. We've proposed an alternative formulation, which we call informative sensing, which I think is a very fun problem to think about. Still open. How do we design an optimal measurement matrix given knowledge of signal statistics? And I think we've solved it for a subset of signal models, but there's still a lot of work, a lot of other signal models that one could look at. For natural images, we've shown that the optimal measurements depend on sparsity. And for most natural images, measuring mostly low frequencies, which is what PCA would tell you, is optimal. However, again, I should say this in defense of the compressed sensing people, for highly sparse natural images, random projections are actually optimal, also according to our theory. And this is certainly surprising. I'm sure nobody before 2006 would have thought to apply random projections to natural images. And there are actually settings for very sparse images like the cameraman. Even according to our theory, this is actually the best thing to do. And maybe a final point of negativity is that because we're restricting ourselves to linear codes, even with optimal projections, you can only expect modest compression gains. Thank you.
So
Yeah.
if you do adaptive, so you're assuming your matrix is fixed.
Right.
Yes, if you choose your first measurement and the second measurement.
Yes, you can do, that's called, okay, I should say one place where this something just like informative sensing has been studied is known as Bayesian experimental design, which is exactly this. You have a set of measurements. Every experiment in this sense is to multiply by a matrix. So you want to test some hypothesis about a distribution, and and you're allowed to do linear measurements. And their sequential experimental design is something that's very well studied, and you can do much better. Certainly, doing them one by one and deciding which projection to do based on the previous ones improves performance by a lot.
But it's not relevant to the camera, to the 1 pixel.
For the 1 pixel camera, I didn't say, but the 1 pixel camera is actually a sequential thing. That's another problem it has. It can't capture moving scenes. It captures 1 pixel at a time. It keeps moving these micro mirrors. Maybe for other applications, like medical imaging, maybe it's really an engineering issue of whether you can afford to measure one thing and then change this imaging setup before the second one comes along. I think both are interesting application domains to look at. For a standard camera, that you want to capture a lot of measurements at the same time. No, you have to do something in advance. Yeah.
So what if you use these three-dimensional cameras they have? They use lots of pixels for one, lots of receptor pixels for one actual pixel of the photo. Do that at really low resolution, and then take a normal 2D one at a medium resolution and use the 3D information to inform the basis that you use to encode the 2D stuff. Would that be better than using a wavelet basis?
Yeah, again, that's an example. It's something similar to what Adam. It's a special case in something that what Adam was saying, because you have some sequential algorithm where you do one thing and then you change the camera. So I'm sure it would be better. Well, there would be significantly better because you have this problem of.
You have to use a lot of pixels so that the 3D one would have to be very low resolution.
And you'd also need to be able to do everything fast enough.
You get a sense of what regions of the image are actually relevant and use those.
Yeah. So I think that's in the same class as what Adam was proposing of doing sequential. And I think for most cameras, you probably cannot afford to do that because you want to take a picture immediately and you don't want to wait. But I think for some medical imaging settings, where the patient's in the MRI machine for, I don't know, for an hour, maybe you can do something. But on the other hand, the hardware there is very difficult to move. So maybe if you figure out the optimal projections, it's hard. So yeah, I don't know. Yeah.
Right, so like in all this stuff and all the the articles on this, it's always power consumption or data and all this stuff. But surely there's a market for like super high resolution pictures. Like say I want to take a picture and I want like I want like 100 gigabyte picture of something to print a wall-sized portrait that's like beautiful.
Okay.
I'm sure there are people or like in old school photography, everyone had these big cameras with huge things, really unwieldy.
Yes.
They wanted to blow their picture up to be wall-sized,
Yes.
or to look like you're looking out a window. And I haven't heard anyone be like, oh, actually, no, we're not trying to save the battery or anything. We're just trying to somehow make it possible to get ridiculously high-resolution pictures out of the lowly, 10 megapixel CCD chip on a camera.
Yes, it's actually right. So
Like
maybe
this-
different.
But I think it's the same issue. I mean, whether you're going from 1 megapixel to 100,000, or going from
No, but it's more saying like
either you can get these compression ratios or you can't, right? I mean, it's not.
no. Like
Why do you think there'll be sort of
you're not
different
gonna?
behavior?
I mean, you're not gonna find a 1,000 megapixel CCD chip for less than, $5 million.
The question is it going to be feasible to do compression?
The kind of compression ratios that you're going to get using natural images are about a factor of 2. I mean, it's the same, assuming that the statistics are the same at these high resolution.
I mean, there's a question like, is the behavior different from the tail versus kind of the head? Because if you're looking at global reconstruction, you kind of see this a lot when doing PCAs. Like, everything, you get a ton by just measuring the image intensity or something like that. But in a sense for this is like, can I look at the image statistics when I've already got most of the image already, and now how good is it to reconstruct kind of the last bit of super high?
I think those are separate questions. Anyway, actually, there was an interesting conference, if you were interested. There was a conference that just ended at Harvard over the weekend called the ICCP, International Conference on Computational Photography. And there are people, so computational photography is this general field that combines computers with cameras and uses algorithms in order to generate. So they were actually demonstrating a camera for taking very high resolution pictures of paintings.
I mean the point
So you can, if the scene is static, there are certainly hardware things you could do that would take an ordinary CCD thing and shift thing and build it back together again.
Yeah, no, I mean the point is like if we only had cameras with a single CCD,
Yes.
then we'd be forced to do if we only had 1 pixel cameras, we'd be forced to do something like this, right?
Yes, but I think the point is, even in that setting, you would not want to do random projections. You'd be better off
Doing something else.
doing something else.
Sure. No, all I'm saying, yeah.
And it's not going to give you, unfortunately, this factor of 1 million. If you want really want high quality, you're not going to get, or acceptable quality, you're not going to get a factor of 1 million. You're going to get a factor of 2.
So why not?
Well, because assuming our signal model is correct, then even under the optimal projection, if you want acceptable quality, you can afford about a factor of 2. Right.
Saving a factor of 2 over just going 1 pixel at a time.
Yeah, but no, the world isn't pixelated. I have a single receptor, and I want a nice image. So what you do a lot of these projections, you somehow recover something or other.
Yes.
There's no factor of 2, like the
Oh,
world.
no. The number of projections you'll end up having to do is equivalent to the resolution you want in the end.
Yeah.
Which is, if you're okay with that.
No, that's fine. And I'm just saying, like, if you could get a camera that says, oh, it's a 100 megapixel camera, although it's only built on a 5 megapixel CCD chip, then cell phone companies would be knocking down your door, presumably.
Yes.
And it doesn't seem so hard to do, right? It's not so hard. And I'm wondering why people aren't really.
Well, I think people do build people have built these things for like digitizing our cultural artifacts. Actually, this is a Microsoft Research Asia project. But I think it really works well when the world is static. Most consumers want to. That's not the killer app for most consumer cameras, right? We want to also be able to photograph things that are moving, and so we can't afford to take lots and lots of pictures.
This is related to that. So you're taking a picture of something moving, and there's sort of jitter now. So now what you get from your linear projection is a time average. Now, do you have an idea of what are good ways to measure if you're sort of getting a blur of the...
Yeah, so the blur really kills the sparsity, unfortunately.
Right, but does it change the types?
So it makes PCA even more, it would make
Actually, makes PCA better.
better, yeah. Yeah, well, I should say one really depressing thing for us. So we have this theory, and we're really looking for an application where we can do much better than PCA using Infomax and these... And it's very difficult to find. We've gone through application after application. PCA is just very, very good. Maybe we'll find something in the end. All right?
Thanks.
Thank you.